In this video, we're going to be taking a look at multi-mass systems that are connected to one another, and we're going to be talking about how to easily and effectively find the acceleration of each of the systems and then find the force of tension as well. Now, there is one key strategy for most of these types of problems, which can pretty much be implemented in just about any case that I remember, and that strategy is clumping everything up into one big system and then figuring out which is your positive and which is your negative direction. So before we step into that main strategy, we want to make sure we go ahead and draw the forces acting on each of our individual masses first. So let's go ahead and start off by doing that. All right, so we have all of the forces that are pushing and pulling on each of these masses. Now, what you're going to want to do is, like I said, our key strategy is clumping everything up into one large system and figuring out which direction is your positive and negative direction. For example, if we're taking a look at this situation over here, we have a block on a table and then a mass hanging vertically off of this pulley, we can take a look at it as one system like this and treat it like one big 7 kilogram mass. And clearly, because of this 4 kilogram mass hanging off the edge and only a little bit of friction, we're just going to go ahead and assume that everything is going to be moving. So we'll say this direction, everything is going to be positive. Now, it's important to identify that because normally you would call it downwards negative. That's a pretty common idea to use in physics. So when you're taking a look at this, everything that's going along this direction, we'll call it positive. So anything that is propelling the system to move. And then anything that's going in the exact opposite direction would be considered negative. So if you go in the exact opposite direction, let's go ahead and change that color. We'll call this all the negative direction. Okay, and then you would do the same thing for all of the other systems. You would go ahead, take it, wrap it up, and treat it like one big 7 kilogram mass. This one, we'll just say everything to the right is positive, and then everything to the left is negative. That one's a little bit more simple. And then this one over here, if we wrap this up and make it a 7 kilogram system as well, this one isn't going to move because it's sitting on a flat surface. So we'll say everything going this way is positive, and then anything going back in this direction is going to be negative. Now, when you do that, you basically just have to analyze the masses in the system and ignore all internal forces. So as of now, for all of these systems, you're going to ignore tension because they're internal forces. They're inside of this green clump right here. So we would just want to take a look at everything that would be affecting the acceleration of the object. So I'll fully work out this top example because I think this one's the most complicated, but we'll also take a look at the other two as well. If we take a look at, say, this system over here, our main driving force is this Fg right here. This is our main positive driving force. And then if we take a look at this 3 kilogram block, the main force that's opposing its motion is this FFK over here. So basically what you're going to do is you would take the force of gravity, which is just mg of the 4 kilogram mass, subtract the force of friction from the 3 kilogram mass, which would be mu k times the normal force, and the normal force and the Fg would actually be the same number. and then that would equal 7 times A. So one of the other keys is to combine your masses and call it one big 7 kilogram chunk. And then that's how you would solve for the acceleration for this particular setup. Okay, this one over here is a little bit less complicated. We have an FT1 of 20 newtons, and then we just have the force of friction from the entire system. So the way that this one would look is we would just have the 20 newtons minus your force of friction of all 7 kilograms in total, because both of the masses are going to be interacting with the surface. And then the opposing slide is going to be, again, this formula right here, the coefficient of kinetic friction times the normal force. So which is basically 0.1 times 7 times 9.8. And that equals, again, 7 times A, the mass of the whole system, times your acceleration. And you would divide both sides by 7 eventually to get your A. So let's go ahead and clear the bottom two scenarios, and then we'll fully work out the one in the top left-hand corner. All right, so what we're going to do is go ahead and find the components of this FG first, because I already can tell that we're going to use it a little bit later. We'll call this the FGX component, and we'll call this the FGY component. And we have an angle from our ramp over here, which is actually 30 degrees that I didn't write in the original picture, which would translate here, and it would be this 30-degree angle in our right triangle that we created from our FG. Now, because it's on an inclined plane, we want to make sure everything is perpendicular or parallel. So we want our FGY and our FGX. Our FGX is opposite of our 30 degrees, and we're going to want to make sure we use the sine of 30 degrees. And sine is opposite, FGX, over our hypotenuse of FG, which is mg, 4 times 9.8. And then we're going to do the same thing for the adjacent side. And we're going to grab cosine of 30 degrees, because that is the adjacent, our FGY side, again, over our hypotenuse, which is FG. FG is mg, 4 times 9.8. Okay, and then we're going to multiply both sides by 39.2, because 39.2 is 4 times 9.8. And then we get our FGX of 19.6. And then we get our FGY of 33.95 newtons. All right, so now we're ready to take a look at the whole entire system. So if we're taking a look at our whole entire system, we have a main force that is driving the 4 kilogram block in the whole system down the ramp, which is our FGX. So we have the FGX driving the entire system, and then everything else is internal or it's perpendicular to the surface, besides the FFK of the 3 kilogram block and the FFK from our 4 kilogram block. So we want to subtract the force of friction from our 4 kilogram block, and then also subtract the force of friction from our 3 kilogram block. Okay, and that's going to equal the whole system of 7 kilograms times A. And you notice I added a little extra subscript there, so I kept my numbers all in order so I know what I'm looking at a little bit later on. So let's go ahead and plug in some numbers and see what we get for this acceleration. All right, so we had our FGX from earlier, which was right over here, and that was 19.6. And then for friction, it is mu times the normal force. Our mu is 0.1 for both of the surfaces on the incline and on the flat part of the surface. So all we need is our normal force. For our 4 kilogram block, our normal force over here is equivalent to our FGY because those are the only perpendicular forces. So those are equal and opposite to one another. So our FGY of 33.95 is our normal force. So that's why I have 33.95 there. For a 3 kilogram block, again, our Fn and our Fg are the only vertical or perpendicular forces. So those are equal and opposite to one another. So Fg, which is 3 times 9.8, gives us 29.4 newtons, which means Fn is 29.4. That's where this 29.4 came from, equals 7 times 8. So I just found the product of these two, subtracted everything, divided both sides by 7, and then I got my acceleration of the entire system, 1.895 meters per second squared. Now, the next thing I want to do is find tension. So we already found acceleration, check. We want to find tension next. So the only way we can do that is now not look at our system as a whole, but take a look at each individual mass. So we can either analyze the 4 kilogram mass or the 3 kilogram mass. It actually really doesn't matter. Both of them would have an FT in it, and these FTs would be equivalent to one another. Just because the 4 kilogram one looks like it's slightly more complex, I'm just going to go ahead and grab the 3 kilogram one. That one looks a little bit more simplistic. So for the 3 kilogram, we have the FT driving it. So that is our positive minus the frictional force, which is again 0.1 times the 29.4, because our 29.4 is our Fg, which is equal to our Fn. And that equals the 3 kilogram mass times this acceleration right here, 1.895. So that one came in handy. And then this is just going to be 2.94. Go ahead and add that to both sides. And then we get our Ft of 8.625 newtons. Okay, so that's the strategy for those multi-system problems. Like I said, you wrap them up into one big system, you find the acceleration first, and then the acceleration proves to be useful later in finding internal forces if you need them, such as the Ft. Again, you could take a look at either one of your masses. I always pick the mass that looks a little bit more simple, and then I just go with that one, but it really doesn't matter. You could also actually find the FT for both of them and see if you get the same number, so you can sort of double check your work as well. So I hope that was helpful to you. Thank you very much for watching and listening.